Now we're solving non-homogeneous PDEs, i.e. eigenfunction expansions. To show how to solve the initial boundary value problem given here, a non-homogeneous PDE can be solved by finding a series solution of this form, where the xn of x are eigenfunctions we find when solving this, and tn of t are functions that can be found by solving a sequence of ODEs. The idea is to solve the equation in the box by a method analogous to the variation of parameters in ODEs, and is known as the eigenfunction expansion method. The solutions with f of x at t equals 0, the corresponding homogeneous problem is given by here, where lambda of n and x of n of x are eigenvalues and eigenfunctions of the Sturm-Liouville problem. I believe I've gone through this before in a differential equations video. These are pretty straightforward to solve, and we have solutions for all of these. So we ask whether the solution of the non-homogeneous problem can be written in the general form given here. The reason for this speculation is physically appealing, inasmuch as a source of heat, f of x of t, within the rod will give rise to a new time component and not the damping factor here. As was the case when the only input into the problem was the initial conditions. Now, to show how this method works, we apply it to a simple problem so that the details aren't as complicated. Now consider the non-homogeneous problem given here in the box. To solve this problem, we divide the procedure into the following steps. Step 1, decompose heat source f of x of t into simple components, i.e. given here, and find the response u of n of x of t to each of these individual components, f of n t, x of n x. So the solution to our problem is then here, given here. To determine how to decompose f of x of t is one of the major problems. It turns out that the xn of x factor is the problem in the problem are the eigenvectors of the Sturm-Liouville system we get when we're solving the associated homogeneous problem by separation of variables, that is given here. And in this case, the Sturm-Liouville problem, we find the separating variables is given here, and hence x of n of x equals sine n pi of x, where n equals 1, 2, and so on. So the decomposition of the heat source as the form f of x t, f1 of t sine pi of t, and notice the pattern here, the 2's and so we're just increasing continuously. Now finally, to find the function f of n of t, we multiply each side of the equation by sine m pi of x and integrate with from 0 to 1 with respect to x. Doing that integration here, it leaves us with this. Now, or changing m to n, we get this. So this will give an equation for coefficients f of n of t in terms of the heat source f of x of t. Now step 2, we find the response u of n x of t equals t of n x of n to input this here. We now replace the heat source f of x of t by its decomposition here, and we try to find individual responses. In other words, we seek the function t of nt, knowing these. The answer to our problem is here. Now substitute u of x of t equals the sum n equals 1 to infinity of t of n of t sine n pi x into the system. We get this here, which gives us this. And so on, plugging in the values and initial conditions, rewriting PDE and initial conditions as this term. I'm sure you can follow the algebra here. Now we can easily see that t of n of t will satisfy the simple initial value problem given here. This equals our a of n term. This ODE is one of the easier ones to solve using the integrating factor and has the solution given here. Hence the solution to the original problem is this. Now this is the transient part and this is the steady state part. Because this is the transient part because of the initial value conditions, and this is the steady state because of the right hand side f of x of t. We can see from this solution that the temperature response is due to two parts. The first is due to this second part. The first is due to the second part, that is due to the heat source f of x of t. I think maybe I've written that right on, I don't know. But yeah, that's the gist of the situation here. It's worth noting, like I've said before, the differential equations video, that we're always trying to get it into a form that can be solved analytically, and Sturm-Liouville are the given standard equations that have widely known solutions. So we're getting this into that kind of form. It makes it easily solvable. Anyway, please do like and subscribe.